Hi, I'm David Cheskis from Trieye, and I'm going to talk today about seeing beyond the visible, how we're delivering high-performance SWIR machine vision solutions. First, I wanted to spend a little time talking about CMOS and Moore's law, and how we got here. So, I looked up Moore's law on Google, and this is what I got. This is the AI overview from Google. Moore's law is the observation that the number of transistors in an integrated circuit doubles roughly every 2 years, and that was done around 1965, and it's been held true for the last, I don't know, I guess that's 60 years or so. And you can see here on the right hand side what that means. That means that as we double the number of transistors, we get bigger and bigger and more powerful microprocessors, and that's held true. You can see that curve that you see on the right-hand side there, that's really going. I think that's also from Wikipedia, and it shows the number of transistors in an Intel processor. So that's been going great. I mean, Moore's law is fantastic, works great. Most of you have probably heard about it. And today we're even at the point where we're progressing so far that this year, in 2024, TSMC is beginning its 2 nanometer process node, which started out in several microns 60 years ago, and now they're down to several nanometers. So it's moving, it's continuing, it's going great, but there is more than that. And we call that more than more. And that's really a diversification of technologies. And you see down the bottom there, a couple different classifications that we put in there, different wafer diameters, different process nodes, different capabilities that you add to it, maybe some different material types that you put in there, and then also advanced wafer level processing. And this is what all enables us to do things that we consider to be more than more. So we can look at different process nodes, different technologies. You've got the 14 nanometer node, a 2 nanometer node on there. That allows us to do, again, that more Moore's law scaling. You can add other types of capabilities like logic, memory, MEMS, SoC, power devices, analog mixed signal. That allows us to do different types of circuits and functionality that doesn't need to scale as much as logic circuits do. You can add different materials like gallium nitride, aluminum nitride, SOI materials, silicon carbide. And again, that gives us additional layer of capabilities. But what's really, really interesting for us, we want to talk about today is advanced wafer level processing. You see that in the purple there. And that includes things like wafer stacking, wafer to wafer bonding, 3D integration. And that's really enabled us to do a lot more in the same area and with different material types on a CMOS platform than we've done in the past. And what that looks like is we want to talk today about how that applies to image sensors. And in the CMOS image sensor space, that's really allowed us to continue to scale with Moore's law down CMOS image sensor scaling. But it allows us to introduce other technology like a BSI, backside illumination technology, or allows us to use things on the back end of the line like multi-level metal, color filters, micro lenses that allow us to not just improve the capabilities, but change the capabilities of image sensors today. But getting back to the scaling, back in 2008, you could really see how the technology node down at the bottom there in green was able to continue to scale with Moore's law. Um, Once we started to introduce the pixel size scaling, you see in the red lines that followed the same path. So we're able to kind of continue down that path there. And the blue line down the bottom is what we call the ITRS roadmap, which is an international consortium that defines where we need to be, when we need to be there for silicon processing. And again, the interesting thing here is that pixel size continued to scale as the technology node scaled, as logic circuits scaled, and it's continuing to scale today. And if as recently as 2021, we continue that line now. It's scaling as the technology node scales for CMOS. We've replaced the roadmap with an IRDS roadmap rather than the ITRS roadmap, but it's still moving forward. We're kind of about 10 years behind what we would like to be with the Moore's law scaling, but the technology node to pixel size really continues to scale at the same rate. And so that's good. And we'll continue to do that. But the question is, what's enabled these capabilities and what do we do next? So when we look at how this has really been enabled, smartphones have really been the driving factor for changes to CMOS image sensor. And this is a chart put together by Yole that really talked about how that has evolved over the last, 10, 15 years or so. You start there on the top left-hand corner and the technology node at the 180 nanometer technology node on a 200 millimeter wafer. And, 2 micron, 3 micron pixel sizes. And as we scale in the future, all of those move to the right and lower. So we get lower technology nodes, we get smaller pixels. But right around 2009, 2010, when we started to move to the 300 millimeter foundry, we started to diverge between what we would do with the pixel and what we would do with the logic and the ROIC. And you see those two different lines there, the red line and the black line. And so what that allows us to do is now discouple or decouple the two technologies so that logic continue to scale as it does with Moore's law. And we use a more than more approach to do in this case, you see a stacked wafer process to do different types of image sensor pixel sizes. And we scale that, and you see a micron and below there as we move forward. So today we're getting as low as, zero point 0.6, 0.65 microns on the pixels, whereas in the logic scale, we're on the 22 to nanometer range, and again, moving to this 2 nanometer range eventually. And so in the future, it's going to diverge even further there. You see in 25 and 27 that we can now make sure that we're scaling the pixels the right way, the right sizes, but we're also changing the logic and using the right logic and scaling that the right way as well. And so again, that's really a combination of Moore's law scaling and more than more with the stacked processes to give us the right technology and right nodes for the image sensors. But so how do we do what's next? What's next for us is really seeing beyond the visible, and that's the SWIR wavelength range. And CMOS image sensors work great. Again, there's billions and billions of them made each year for cell phones, for automotive, and most of them are made out of silicon material. And what you can see here is why that's the case. You look here at this curve shows you the absorption rate of photons in silicon. It works really great, 400 nanometers, all the way up to about 1,000 nanometers. And the visible wavelengths from 400 to 700 nanometers, all CMOS image sensors. Near infrared image sensors, again, extended range up to about a micron there. You can also make them in silicon. So a lot of the 3D sensing that gets implemented at 850 nanometers or 940 nanometers is also done using CMOS image sensors. But how do you get beyond there? How do you get to that longer wavelength range to use SWIR? What are our options? So one of the first options is InGaAs, and you can see the curve for the absorption of photons here works really great in that 1 micron to 1.6 micron range. And that allows us to do a lot of things and seeing in the SWIR range. I'll show you some examples of what that looks like. It's really the gold standard for SWIR imaging. But it comes with a lot of drawbacks and limitations. And that's why we're exploring new technologies like germanium. Germanium is shown on this curve here. So it works well in the visible spectrum, but it works really, really well also in that in the SWIR spectrum between 1 micron and 1.6 micron, where InGaAs works well also, but CMOS doesn't work at all. The benefits of using germanium are that you can really use it on a CMOS platform, whereas with InGaAs, you need special materials, special wafers, special fabs that aren't conducive to volume scaling and low prices. And we'll talk about why that's important in a minute. But I just wanted to show some examples of what that looks like. So seeing beyond the visible means what you can see here on this page. On the top, on the right-hand side, we've got some beads and some other foreign objects in there that are all black, and the visible camera, you really can't see much of a difference. Imagine a machine vision camera that's trying to detect these and sort these. It really has a hard time doing that. But when you move to the SWIR image on the left-hand side there, you can see a distinct difference between these different objects because they're made out of different materials. And that's what you see in SWIR is you see material differences, not differences in color. And that really helps us also in a lot of food sorting applications. An example is shown at the bottom here, where we look at apples in the visible spectrum, and they all look great, nice, ready to eat. But when you look at them in a SWIR spectrum, you'll notice that there's some black spots on there that you can't see in the visible spectrum. And those black spots are really bruises under the surface, under the skin of the apple. And nobody wants to bite into an apple with a bruise on it. So we can use these kinds of technologies and machine vision capabilities to sort out good food versus bad food. It's used all the time. So that's what SWIR does for us pretty well these days. And again, a lot of those cameras that are made today are using InGaAs. We want to talk today about what it looks like to do it in germanium, because InGaAs is really a barrier to mass production. Again, InGaAs is not made on silicon. It's not made using CMOS. It's exotic materials. They don't scale the same way. InGaAs is typically made on 3-inch or 4-inch diameter substrates, so 75 to 100 millimeter substrates. compared to CMOS, which can be made on 200 millimeter, 300 millimeter substrates. So you've got a much better manufacturing platform with CMOS. You've got much higher yields. InGaAs tends to be complex, time consuming, and process limited in terms of the resolution and size of the chips. And because of that, you see there, it costs more than $10,000 for some InGaAs sensors. And that's even at a VGA resolution and even more for a megapixel or more. And so what that does is really limits the use case for InGaAs sensors to very high performance, expensive applications like you see on the left-hand side there, defense, aerospace, science. There's not many of them made every year, especially compared to CMOS image sensors for automotive and mobile phones. But because of that, they can handle the high cost points and prices. But what we can really do today is take an image sensor, make it on a CMOS platform with 1/10 the cost of an InGaAs sensor, and really enable these machine vision applications, like we said before, food sorting, inspection, security, medical, where there's volumes and capabilities that you need in SWIR. And so there's machine vision applications today using InGaAs. It's just there's not that many of them because the cost is so high. And what we're trying to do is enable more machine vision applications with a lower cost sensor with the same performance. And these are a couple examples of where you'll see those machine vision systems with SWIR. So machine vision, you see the left-hand side there, you've got different colors. You can see those in the visible. When they all have the same color, you want to identify them differently. You need a SWIR capability. It allows us to do things like robotics and logistics and smart farming with food inspection and recycling. All of these different applications really take advantage of SWIR because SWIR allows you to not see visible, but see the materials, be immune to environmental conditions, and also work in eye safe conditions. And one of the new applications we've started to see developing for SWIR is 3D line scanning. And again, that takes advantage of a lot of the different capabilities that you see in SWIR that really mitigate the issues that we see today in the visible spectrum. And so how do we address that future today? What we've done is we've combined the CMOS and essential manufacturing platform with the capability to do SWIR wavelengths using the germanium materials. And we put that into a sensor we call Raven. And that's our CMOS-based high-definition SWIR image sensor. And we've developed a breakthrough technology that allows us to use SWIR imaging for high-volume CMOS manufacturing capabilities to deliver that performance and low cost. So that's what we're doing today. And I want to talk a little bit about how that works and show you what that looks like. So if you look at something, what Tower talks about is, you've got this CMOS sensor back in the middle of the chart there, a standard CMOS manufacturing platform, and there's a whole bunch of different capabilities you can put on top of that. They list some of these here, organic sensors, quantum dots, a different functionalized layer that includes maybe microfluidics, or this germanium layer as a SWIR semiconductor that we've developed specifically for these SWIR imaging applications. And so this is how it works in a particular platform. Again, because we're using CMOS, there's a whole bunch of different options you can do with this, like we talked about before. And it fits, the germanium platform fits directly into existing CMOS image sensor manufacturing platforms. And this is something that might look like. So what this kind of shows here is how you can implement that in theory. You've got this wafer at the bottom there. We've got two wafers kind of back to back on top of each other. You see on the left, one is the ROIC wafer, the other is the sensor wafer. We can put them together with this wafer level stacking. It looks like a lot of other wafer level stacking processes that are used every day in image sensors and other logic applications. And then on the top there, you see the imaging pixels in green and micro lenses on top of them. And so this is what you can imagine that would look like by taking two different wafers with different capabilities, doing a more than more kind of process application, and giving you this different capability that you can't get elsewhere. And that's how we're doing this to create a SWIR CMOS-based image sensor. And so what does that mean? Let's talk a little bit about what we've done with that. And so we've taken this Raven manufacturing platform. We've created a chip called the TES200, and that's our first CMOS-based image sensor. Again, because we've designed it to operate in the SWIR wavelength range, it goes all the way from 700 nanometers to 1650 nanometers. With the CMOS image sensor, we can get small pixels. We can do 1.3 megapixel resolution in a relatively small image sensor size, about 9 millimeters by 7 millimeters, and package it in a standard 13 millimeter IBGA package. So again, this looks like any other CMOS image sensor with the exception of the fact that it will work all the way through 1.6 microns. And what that allows us to do, again, some other examples of that, you see the same pictures we showed before of the apples and the beads, but then at the bottom there, you see other examples of machine vision systems, which is coffee beans on the left there with some other foreign objects in there, hard to detect in the visible spectrum, very, very noticeable in the SWIR spectrum, and a real classic example of sugar and salt on the bottom right, which again are difficult to see when you're at the dinner table. But when you have a SWIR camera, it's very easy to see the differences between sugar and salt there. And so that really gives us the advantage of what we're doing today with this SWIR-based technology. It's you get this complete vision over all these wavelengths. We're delivering it with a much, much lower cost and a scalable manufacturing platform. And that allows us to do all these SWIR capabilities with remote material sensing, all kinds of different environmental conditions, wide spectral range in the HD, eye safe, and allows us to bring all those advantages of the CMOS-based sensor, which is the low price, the high resolution, manufacturing reliability, small form factor, and lightweight. And that's how we are able to take advantage of these two capabilities and deliver this SWIR imaging on CMOS. So that's what we're doing today. And, one of the things I wanted to address today was also, what does the future really look like for this? Again, more than more allows us to do a lot more things. And we're able to continue to do that. But to first set the stage for that, what we're doing here today is in today's trend for these sensors, it's really RGB with depth and using near infrared as a 3D sensing technology. It's ubiquitous, it's low cost, it's all built on CMOS, and there's a lot of people using it. You can buy it anywhere. You can buy it pretty cheap. And people are using it. They're getting deployed everywhere. It's super low cost and has a lot of great capabilities. But because we're able to do that, especially in machine vision systems, we're starting to see the limitations associated with that capability, that technology, and specifically those wavelengths. And so what we want to do is we want to continue that high volume, low cost manufacturable technology with CMOS based SWIR sensors, but again, provide that additional wavelength capability to go all the way through 1.6 microns. So these CMOS based SWIR sensors in the future will remove all of the current restrictions of these CMOS image sensors today and provide it with a manufacturable, scalable, and high performance platform for these sensors. And that allows us to, again, see beyond the visible. And what do we do with that? Again, it's a factor of integration that we're doing today. We're going to do it with more integration. We've already done some demonstrations of additional lenses using metasurfaces at 1380 nanometers. We've partnered with a company called NIL Technology, and they developed this meta surface optics. They've developed a lens here that allows you to do low cost, scalability, small volume, and really deliver the same performance that they're delivering. That today we're using conventional lenses, but we're delivering this on a manufacturing platform similar to CMOS with, like I said, low cost and high volume. And that's really an enabler in terms of more integration. And then when we put all of that together, I'm going to step back and talk a little bit about what that current near infrared camera solution looks like. And you can see here on the right-hand side, we've got a couple different components to that. So one of them is the near infrared image sensor there in purple. We've got some conventional lenses that go on top of that to make sure we're focusing properly. We've got the ROIC or image signal processing chip. And we put them all together. You see the size, the height, the thickness, all those different components leads to, a non-ideal solution, but that's where we are today. Now, what we can do with SWIR is we can now start to do this all on wafer level integration with a stacked SWIR camera solution. So we can do the meta optics lens, we can do the SWIR image sensor, we can do the processor all together in one chip and deliver that on a substrate at much lower cost, much smaller size, much more reliable. And using these advanced silicon manufacturing platforms, it creates the solution that has all of these components, bringing smaller size, thinner outline, and lower cost. So that's what I wanted to talk about today. Key takeaways for this talk, low-cost SWIR imaging is here today. If you want to see more information about that, go to our website. We've got all the information you need there. You can order parts, you can order samples, you can order dev kits. Elsewise, CMOS-based SWIR image sensors combine the best manufacturing platform with advanced sensing technology that's really going to meet the future demands. We've got a good scalable platform to go out and deliver that. And what we've done here at trieye is we've really revolutionized industrial machine vision sensors that enable the cost reduction and mass production for future applications.